Hello students, when a charged particle enters in a magnetic field, it experiences a deflecting force F, and this force is given by a specific formula. If we consider the charged particle enters in a magnetic field with velocity v, and in a magnetic field of intensity B, then the deflecting force is given by F is equal to QV cross B. Okay, that is, in other words, you can say F is equal to QVB sine theta. QVB sine theta. So this is the deflecting force. Simply you say it is the magnetic force experiences when a charged particle enters in a magnetic field. Dear students, if you see this formula carefully, and if we take V is equal to 0, then we'll find F is equal to also 0. It means when a charged particle is not in motion, when a charged particle is stationary, then it will not experience any magnetic force. Okay, and the second thing, if we say sine theta is equal to 0, or simply you can say theta is equal to 0, in that case also F is equal to 0. F is equal to 0. So if a charged particle enters in a magnetic field along the same direction of magnetic field, then it will not experience any force. From this concept, you can define the magnetic direction of the magnetic field. Okay, so magnetic field you can define like this also. Direction of the magnetic field: if a charged particle moving through a point in a magnetic field B does not experience a deflecting force, then the direction of motion of particle is the direction of B at that point. So this is a definition. What is the direction of the magnetic field? So that is a direction in which charged particle does not experience any deflecting force. In other words, you can say direction of the magnetic field is that direction in which a charged particle does not experience any force. So from here you can see B is equal to F upon QV sine theta. If we put the values, suppose take the unity of all these to find the unit of B from this formula. So it is 1 Newton, 1 Coulomb, and speed is 1 meter per second, and take sine theta is equal to 1 because when it enters at 90 degree. So you can say Newton per ampere per meter. Okay, so that SI unit of magnetic field is also Newton per ampere per meter. Okay, It is also known as the Tesla. It is equal to the 1 Tesla. Tesla is the another unit, and another unit of the magnetic field is Weber per meter square. Weber per meter square. So basically we will use only 3 units of the magnetic field: Newton per ampere per meter, Tesla, and the Weber per meter square. Okay, its dimension you can find from here. From here you can find see dimensions of F upon QV, because sin theta is the dimensionless. F upon QV, F means force MLT minus 2, and Q means the Q is equal to IT, AT, and V means LT minus 1. So dimensions of B is MT minus 2, A minus 1. Okay, so it is the dimension of B. Okay, so this is about the introduction of the magnetic field, directions, and what is the magnetic field. Now we are moving to a very important topic, that is the motion of the charged particle in uniform magnetic field when enters. See what will happen. So see the next topic, important topic, you can say motion of charged particles in uniform magnetic field. Okay, here we assume a charged particle enters in a magnetic field which is perpendicularly downwards direction. I am showing a magnetic field, uniform magnetic field, perpendicularly downwards. Okay, perpendicularly downwards, and a charged particle enters here. Okay, suppose like this, enters. Okay, enters like this. So suppose this is the direction of charged particle, positive charged particle I am showing here, positive charged particle. This is the direction, this is the direction, this is the direction. It is moving on a uniform circular motion. It is the V, it is the V, V, and it is the V. Okay, so because it is the direction of positive charged particle, so it will be the direction of the current also. If it is the direction of the current and the direction of the magnetic field is given, so we can find the direction of the magnetic force also by using the Fleming's left hand rule. Okay, so I am showing here, just remember, this is the force, this is the magnetic field direction, and this is the current. Okay, so here I am taking the V in the direction of V, this one. Okay, it is the direction of V, direction of positive charge particle, that is the current, direction of the current. Magnetic field is perpendicularly downward. So what will be the direction of force? It is towards the center of the circular motion. Okay, like this. This is the direction of force here. Okay, if we take here any point, suppose here I am taking, so this is the direction of current, force will be towards the center. It is the B, it is the I, so direction of force is in this direction. Okay, and similarly here, by using the Fleming's left hand rule, we can show that every time the direction of the magnetic force is towards the center of this circle. So we know the force is equal to QVB, and this force will be balanced because it is moving on a circular path. It is equal to the centripetal force. Okay, because only the centripetal force compels a body to move on a circular path. So here we can write it is equal to QVB, and I'm not taking here sine theta because theta is equal to 90 degree. It is perpendicular. Okay, it is perpendicular because it enters perpendicularly in the magnetic field. So it is equal to centripetal force mv square upon b. So from here you can see mv square upon r. So r is equal to mv square upon qvb, or we can write r is equal to mv upon qb. One v is cancelled here, so this is the r is equal to, that is the radius of the circular path. Okay, so you can say here the radius is directly proportional to the momentum. Okay, it is the momentum, that is the p, directly proportional. Okay, if it comes in your exam to prove that in a circular path, when a charged particle enters perpendicularly in a magnetic field, its radius is always directly proportional to the momentum. Okay, you can express this in terms of the kinetic energy also. We know K is equal to half mv square, and from here we can write V is equal to 2k upon m under root. Okay, so if we put here V is equal to this value, so we'll find R is equal to under root 2 mk upon qb. So this is the expression in terms of the energy, kinetic energy. Okay, this is the radius. Now we can find this in terms of the time period also. See what is the time period of the charged particle which is moving here. So to find the charge time period, t is equal to t is equal to 2 pi r upon v. Okay, total distance upon speed, t is equal to. So from here if we write r upon v, from here see what is the r upon v. R upon v is equal to, it is the m upon qb. R upon v is equal to m upon qb. Clear? So now put here r upon v is equal to m upon qb. So we'll find t is equal to 2 pi m upon qb. So dear students, this is the time period of the charged particle which is moving in a uniform magnetic field. And frequency, what will be the frequency? Frequency, that is the 1 upon t. So it is equal to qb upon 2 pi m. Is it clear? So you know the formula of the frequency and the time period right now. Students, a question arises at this stage: why the time period and the frequencies do not depend on the radius of the circular path, independent of the r? Why it is not depending on the radius of the r? Okay, or not depending on the v? Okay, it question arises. So the answer is that actually r and v both are auto-adjusted in this process. It means when the time period increases, the charged particle start moving on a larger radius path. Okay, it increases, and the same times v decreases. So r and v both are self-adjusted. Okay, when R increases, V decreases, so that this ratio remains always constant. In other words, you can say the R directly proportional to V here, always. And from here it was also clear. If you see, radius is directly proportional to mv, so R is always directly proportional to V here. So that's why when time period increases, radius also increases and V decreases. Okay, and vice versa in the case of the frequency. So this is about the motion when a charged particle enters in a magnetic field. When suppose, now I'm taking a special case, suppose the charged particle is not enters perpendicularly, that is at 90 degree. Okay, it is not entering. Suppose I'm taking the example, it is at particular angle. It is at particular angle, suppose at angle theta. Then what will happen? In that case, this magnetic, the direction of the motion of the charged particle can be resolved into two factors, into two components, that is the V cos theta and the V sin theta. Okay, if it enters not 90 degree, so it is V cos theta and V sin theta. So V sin theta, what will try? It will try to move the charged particle always in a circle, in a circular path. It will try this component, but this horizontal component will try to move the charged particle linear. So two components, that is the V perpendicular, it is the V sin theta, and the V parallel, it is the V cos theta. And the resultant of these two will be in the form of the helix. Okay, helical path, like this helical path. So its radius of the helical path is given by R is equal to m V perpendicular upon QB, or you can say the mv sin theta upon QB. Okay, and the time period is the same, 2 pi m upon QB. So what will be the value of the pitch? Pitch means, suppose this is the one circle, this is the second circle, this is the third circle. So you can see there is a linear displacement. In after every one circle, it moves on a circular path. It covers a linear path. That is known as the pitch. So see, what is the value of the pitch? Value of the pitch, you can say it is the parallel, because only the parallel component, that is the cos theta, will cover. Due to this parallel component, the charged particle covers a linear distance. So V parallel into time period t. So we can write V cos theta, and t, it is the 2 pi m upon QB. 2 pi m upon QB. So this is the you can say pitch. The value of the pitch you can find from the formula. Okay, now we can discuss some more points about the motion of the charged particle, like the kinetic energy of charged particle. How can we find the formula? Of the kinetic energy of the charged particle? You know, kinetic energy is equal to half mv square, and just we have a formula, R is equal to mv upon qb. So put this value, since R is equal to mv upon qb, so put here, so k is equal to half m, so mv put here, better write the V from here, write the V. So V is equal to Q B R upon M. Q B R, V is equal to Q B R upon M. Okay, now putting the V here in this formula, mv square upon mv square. So V square means QB R upon M square. Okay, so we can write K is equal to, it is the R square Q square B square upon 2, and 1m is cancelled here, 2m. So this is the formula of the kinetic energy useful in numericals, like in 2020 examination this year. We have a numerical based on this formula. Okay. Now, one more thing about the force you should know, that is, what is the Lorentz force? What is the Lorentz force? Okay, one term you should know. Actually, when a charged particles enters in a magnetic field where the both fields are there, that is the magnetic field and the electric field, then the combined force on the charged particle is known as the Lorentz force. You know, electric force is equal to QE, and the magnetic force it is equal to QV cross B. Okay. Now when both are combined, so we can write F is equal to Q E plus V cross B. Okay, so this is known as the Lorentz force. So sometimes very useful in numericals. Dear friends, after this, in next video we'll discuss about the cyclotron, a very important device to accelerate a charged particle in a given magnetic field. Thank you, students.